At the heart of the Virgo galaxy cluster lies a monster, the supermassive black hole of M87, billions of times more massive than our Sun. How does such an object shape entire galaxies, and what secrets is it still hiding? Stay with us as we explore this cosmic giant. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, what's the first question you'd ask about a black hole? Thank you for watching. Now, let's begin. The Virgo cluster spreads across a region of space tens of millions of light years away, and it stands as one of the nearest and most massive clusters of galaxies to the Milky Way. When seen through telescopes, it contains more than 1,000 galaxies bound together by their mutual gravity. These galaxies are immersed in a vast envelope of diffuse gas that is heated to tens of millions of degrees and glows in X-rays. The cluster is not an evenly arranged group, but a complicated gravitational system with dense knots of galaxies and long arcs of material, showing signs of past interactions and ongoing mergers. Within this crowded environment, some galaxies appear stretched and distorted, a signal that close gravitational encounters have shaped them. At the cluster's center lies M87, also known as Messier, 87, the brightest and largest member of this collection. M87 dominates its surroundings with both its size and its influence, extending a gravitational pull across a wide region and anchoring the cluster dynamically. M87 is not a spiral like the Milky Way, but a giant elliptical galaxy. Unlike spirals which display ordered disks of stars with arms winding outward, ellipticals are diffuse, roughly spheroidal systems. M87 has no sharp edge. Instead, its stellar light gradually fades with distance from the core. The galaxy's halo extends for hundreds of thousands of light years, containing countless old stars. This halo is so extended that small satellite galaxies orbit within it, almost as if they are part of the main system. Globular clusters, which are tightly packed groups of ancient stars, surround M87 in remarkable numbers, with estimates reaching more than 10,000 of them. These clusters trace a history of early star formation and mergers that built the present-day galaxy. Observed through different filters, M87 shows predominantly yellowish starlight, a clue that its stars are old and lack the blue tint of younger, more massive stellar populations. The Virgo cluster environment exerts a strong effect on M87. The hot intracluster medium presses against the galaxy's own gas. Streams of stripped material are seen in many neighbouring galaxies, but M87 itself is massive enough to retain a reservoir of hot gas. This gas is detected through its emission in X-rays captured by observatories such as the Chandra X-ray Observatory. The gas fills the central regions of the cluster extending around M87 in a glowing atmosphere. Ripples, cavities and shock fronts mark this hot medium, and each of these features carries the signature of powerful outflows from the galaxy's core. These outflows are linked to activity driven by the supermassive black hole, although the details of how the energy is injected remain an area of study. When astronomers measure the total mass of the Virgo cluster, they find that the visible galaxies and hot gas account for only a fraction. The majority of the mass is invisible and is attributed to dark matter. The distribution of galaxies, their orbital speeds, and the confinement of hot gas together reveal that unseen matter must provide the gravitational glue. This hidden mass dominates the dynamics of the cluster. M87 at the heart of the cluster sits within this extended dark matter halo. It is therefore both a galaxy in its own right and a key gravitational anchor within the wider cluster environment. Looking more closely at M87 with optical telescopes, astronomers find a bright central region that outshines any individual star. This bright core does not behave like a simple collection of stars. Early in the 20th century, careful measurements of light from this central zone revealed hints that something unusual was present. Later, detailed spectroscopy showed that stars close to the nucleus move at extreme velocities, in some cases hundreds of kilometers per second. Gas clouds near the core also display rapid motions, shifting spectral lines in ways that cannot be explained by ordinary stellar mass alone. These findings pointed to the existence of an unseen compact mass located at the center. The idea that a supermassive black hole resides within M87 gradually gained evidence, and by the late 20th century, dynamical studies placed the central mass at several billion times the mass of the Sun. Unlike stellar black holes which form from the collapse of individual stars, supermassive black holes are thought to have grown over cosmic time through mergers and the steady feeding of gas. The one in M87 is among the most massive known in the nearby universe. Its immense gravity affects not only the motions of nearby stars and gas, but also the large-scale behavior of the galaxy's environment. From Earth, the distance to M87 is roughly 55 million light-years. This means that light seen today left the galaxy when early primates were beginning to evolve on our own planet. The scale is vast, yet the black hole at its center can be studied in remarkable detail because of its mass. The gravitational radius of a black hole scales directly with its mass, so the larger the black hole, the larger the shadow it casts against background light. For M87, the event horizon spans a region wider than the orbit of our solar system's planets. This size, combined with the galaxy's relative proximity compared to more distant quasars, makes M87 an ideal candidate for direct imaging experiments. In addition to its central core, M87 displays one of the most striking features known in extragalactic astronomy, a jet of plasma launched from the nucleus and extending for thousands of light years. This jet is visible in optical light radio waves and X-rays. Through telescopes, it appears as a narrow, bright line emerging from the core and gradually broadening. The jet is aligned roughly toward Earth, though not directly allowing astronomers to trace its structure along its length. Knots and bright regions within the jet mark areas where particles are accelerated and radiate strongly. The presence of this jet is one of the most direct signs that the black hole is not a passive object, but an active engine transferring energy outward. The Virgo Cluster with M87 at its center thus provides a laboratory for understanding how black holes influence their environments. Observations show that energy from the jet and outflows creates cavities in the surrounding hot gas. These cavities rise like bubbles through the cluster medium, displacing hot plasma and transferring heat. By doing so, they help prevent the gas from cooling too rapidly and forming new stars at rates that would otherwise exceed what is observed. In this way, the central black hole in M87 regulates not only its host galaxy, but also the cluster environment. The balance between cooling and heating is delicate and is still the subject of research, yet the overall picture demonstrates that black holes are central players in galaxy evolution. All of these details form the backdrop for the focused studies of the black hole itself, often referred to as M87 star, or simply the supermassive black hole of M87. Its mass, its event horizon, the structure of its accretion flow and the origin of its jet are the subjects of continuing exploration. Each new observation adds a piece to the picture, and each unanswered question guides future research. M87 as an elliptical galaxy appears different from the structured and familiar spiral form of the Milky Way. Its stars are arranged in a smooth spheroid lacking spiral arms or a thin rotating disk. The galaxy's light is diffuse, gradually fading outward rather than ending with a sharp boundary. The central region is especially bright, and from there the glow spreads across a halo that reaches hundreds of thousands of light-years in radius. Within this extended envelope lie countless old stars. Their combined emission is what gives M87 its golden appearance in visible light. This colour signals that the population is dominated by older, lower-mass stars rather than the blue, luminous stars that define spiral arms in galaxies still forming stars. The absence of young, bright stellar populations tells astronomers that star formation in M87 has been largely quenched for billions of years. Around this galaxy floats a swarm of globular clusters. These dense spherical collections of stars are relics from the early universe. They orbit in great numbers, and surveys using the Hubble Space Telescope and large ground-based instruments suggest there may be more than 10,000 of them. Each cluster contains hundreds of thousands of stars tightly bound by gravity, and together they trace the assembly history of M87. The abundance of globular clusters indicates that M87 experienced numerous mergers and periods of intense star formation in its youth. These clusters now act as beacons, allowing researchers to map the galaxy's gravitational field and to study its structure far beyond the visible starlight. The galaxy itself does not exist in isolation. It resides at the gravitational center of the Virgo Cluster, a dense aggregation of galaxies and hot gas. This environment has shaped M87. Over cosmic time, smaller galaxies have fallen in their stars, assimilated into the smooth halo, while their gas was stripped away by the hot intracluster medium. The outer regions of M87 therefore contain evidence of cannibalized systems. Faint streams of stars, sometimes visible only with deep imaging, record these past encounters. The overall effect is a galaxy that grew not by steady in situ star formation, but by consuming neighbours, an outcome common for the largest galaxies and clusters. Viewed through X-ray observatories, M87 is not only a stellar system, but also the centre of a glowing atmosphere of hot plasma. This plasma fills a region many times larger than the visible galaxy, and reaches temperatures of tens of millions of degrees. Its glow comes from electrons colliding with ions, producing bremsstrahlung radiation in the X-ray band. Within this atmosphere are cavities and arcs features carved by outflows from the galaxy's nucleus. These cavities rise through the hot gas like bubbles, showing that the central black hole injects energy on scales that affect the surrounding cluster medium. The interaction between these outflows and the intracluster gas prevents rapid cooling that might otherwise lead to a burst of star formation. Thus, the galaxy's central black hole, though occupying only a tiny fraction of the volume, controls the fate of the entire system's gas reservoir. The sheer size of M87 is difficult to imagine. Estimates of its stellar mass run into the hundreds of billions of solar masses, and its overall gravitational influence is even larger when dark matter is included. The galaxy's diameter surpasses that of the Milky Way by several times. Its brightness is such that it can be seen with modest telescopes from Earth, appearing as a faint elliptical glow within the Virgo constellation. Despite its distance of more than 50 million light-years, the galaxy's bulk ensures it stands out even to amateur observers. Professional studies using spectroscopy and photometry have catalogued its stellar populations, the metallicity distribution of its stars and the kinematics of its outer halo. Each of these measurements adds to the picture of a massive old and largely quiescent system. The morphology of M87 reveals clues to its past. Unlike disk galaxies that rotate with ordered motion, the stars in M87 move in more random orbits. Their velocity distribution reflects the complex history of mergers that built the galaxy. Some evidence points to anisotropies in the outer halo, likely remnants of disrupted satellites. Yet the inner regions appear dynamically relaxed, indicating that the central body has had time to settle into equilibrium. The smooth light profile follows what astronomers call a de Vaucouleurs law, typical for elliptical galaxies where brightness falls off steeply with radius. High-resolution imaging with the Hubble Space Telescope has allowed detailed modelling of this profile, confirming the classic elliptical structure. One striking aspect of M87 is the absence of significant dust lanes or cold gas clouds. In spiral galaxies, dark patches of dust are common, absorbing starlight and signalling regions of ongoing star formation. In M87, such features are rare. The interstellar medium is dominated by hot X-ray emitting gas, not by cold molecular clouds. This explains the lack of new stars and the dominance of old populations. The transition from an actively star-forming system to this quiescent state is tied to the feedback processes from the central black hole. Energy released by accretion and jets heats or expels gas, halting the cycle of cooling and star formation. Thus, the structure of M87 cannot be separated from the influence of the object at its centre. Astronomers have also studied the distribution of planetary nebulae within M87. These glowing shells of gas mark the final stages of Sun-like stars. By measuring their velocities, researchers gain insight into the kinematics of the outer halo, where individual stars are too faint to track. The planetary nebulae confirm that M87's halo extends far into the cluster environment, blurring the line between galaxy and intracluster space. Some stars may not be bound exclusively to M87, but may instead wander the cluster as part of the diffuse intracluster light. This suggests that the true boundary of the galaxy is hard to define, and that M87's growth has been deeply entangled with the cluster as a whole. The gravitational field of M87 bends light from background objects, a phenomenon known as gravitational lensing. Though not as dramatic as in some massive clusters, lensing by M87 provides an independent measure of its mass distribution. Studies of weak lensing patterns confirm that dark matter dominates the outer halo. These observations reinforce the view that visible stars represent only a small fraction of the total mass. The unseen dark matter halo gives M87 the gravitational strength to hold its satellites and to influence the orbits of neighbouring cluster members. The central region of M87, while bright, holds mysteries that extend beyond the stellar component. Astronomers using spectroscopy detect emission lines from ionized gas near the nucleus, and these lines show shifts corresponding to high velocities. Such measurements were among the first hints of an extraordinarily massive dark object hidden at the core. This theme will become more evident in subsequent explorations, but even at the scale of the whole galaxy, the structure points inward, drawing attention to the extraordinary central engine. Thus, M87's elliptical structure, its smooth halo, its rich system of globular clusters, its absence of young stars and its interactions with the cluster environment all frame the setting in which the central black hole exerts its influence. The galaxy is a massive, old and largely quiescent system, yet it is far from inactive. Its structure carries the imprint of cosmic history of mergers and feedback, and of the complex gravitational environment of the Virgo Cluster. The first clues that something extraordinary lurked within the core of M87 came from close study of its stars and gas. When astronomers began to measure the motion of stars near the nucleus, they found velocities that were unexpectedly high. Stars orbiting so quickly required the presence of a huge amount of mass confined within a relatively small volume. The evidence was not visible as any luminous cluster or compact object that could be resolved. Instead, the mass was inferred from its gravitational pull. This approach, known as stellar dynamics, involves mapping the distribution of stellar velocities and comparing them with models of possible mass distributions. The results consistently pointed to an invisible mass far beyond what could be explained by normal stars alone. Gas provided an additional line of evidence. Spectroscopic observations revealed emission lines from gas near the nucleus, and these lines were broadened and shifted in ways that corresponded to rapid motion. Gas clouds were seen streaming at hundreds of kilometers per second. Such motion again implied a central object with enormous gravity. Because no visible star cluster or nebula could account for this, the idea of a black hole became the leading explanation. The notion of black holes had already been explored theoretically through the equations of general relativity, but M87 offered one of the first compelling extragalactic cases where such an object appeared necessary. Radio astronomy added further support. In the mid-20th century, M87 was detected as a strong radio source. The emission came not from ordinary stars but from highly energetic processes. Radio maps showed a bright core and a jet extending outward, features that hinted at a compact central engine. Jets of such scale and power could only be launched by an object capable of focusing enormous energy. This reinforced the interpretation that a black hole was present, one capable of shaping its environment far beyond the scale of ordinary stars. X-ray observations built a more detailed picture. With space-based observatories, astronomers detected hot gas around the galaxy and signs of cavities carved by energetic outflows. These features were difficult to reconcile with any source other than a central engine that released tremendous power episodically over millions of years. By tracing the extent of heating in the cluster, gas scientists could estimate how much energy had been deposited. The amounts matched what would be expected from accretion onto a black hole of billions of solar masses. Thus, independent observations across the spectrum converged on the same conclusion. Over time, measurements grew more precise. High-resolution spectroscopy of stars close to the nucleus revealed detailed velocity distributions. These were compared with dynamical models that tested possibilities such as dense clusters of neutron stars or other exotic compact objects. In every case, the models failed to reproduce the data unless a supermassive black hole was included. The object had to be massive, compact, and dark. No other known astrophysical explanation matched all the constraints. By the end of the 20th century, consensus emerged that M87 contained one of the most massive black holes known in the nearby universe. Estimates placed its mass at several billion times that of the Sun. Later refinements using more advanced instruments and improved modeling techniques narrowed this to roughly 6.5 billion solar masses. This number is astonishingly large, far exceeding the black hole at the center of the Milky Way, which weighs in at only a few million solar masses. The central mass in M87 became one of the best established examples of a supermassive black hole. The idea that such an object could exist was supported by theory. General relativity predicts that when mass is concentrated beyond a certain density, it collapses to a singularity surrounded by an event horizon. For stellar black holes formed from supernova explosions, this requires only a few solar masses. But the same principle applies at larger scales if enough mass can accumulate. Observations of quasars and active galactic nuclei in the distant universe already suggested the existence of supermassive black holes powering luminous outbursts billions of light-years away. M87 provided a nearby and accessible case allowing detailed study of a phenomenon that shaped galaxy evolution on cosmic scales. The presence of the black hole was also consistent with the jet. Jets are thought to arise from processes near the event horizon, where magnetic fields and accretion flows interact. Only a compact and extremely energetic object could launch matter at speeds approaching that of light, and sustain the flow for thousands of light years. In M87, the jet is visible even in optical light, making it one of the most studied examples in astronomy. Its existence is powerful evidence for an active and massive central engine. The combination of stellar dynamics, gas dynamics, radio imaging, and X-ray observations therefore provided a compelling case. Each line of evidence alone pointed toward an unusual mass, but together they painted a consistent picture. The black hole at the center of M87 is not just an abstract concept, but a physical entity whose presence can be measured through multiple observational techniques. This convergence of evidence is what makes the case robust. The significance of these discoveries extended beyond M87. They helped establish the paradigm that most, if not all, massive galaxies harbor central black holes. By demonstrating that an elliptical galaxy like M87 contained such an object, astronomers could infer that black holes are a common outcome of galaxy formation and evolution. The link between galaxy bulge mass and central black hole mass, observed in many systems, gained credibility from cases like M87, where the measurements were clear and convincing. Despite the strength of the evidence, uncertainties remain in details. The precise distribution of mass within the inner parsec, the effect of anisotropies in stellar orbits, and the influence of dark matter all add complexity to the models. Yet even when accounting for these uncertainties, the conclusion remains the same. An invisible object of several billion solar masses dominates the core. The interpretation as a supermassive black hole is consistent with all known physics and observations. Today, M87 serves as a cornerstone example in the study of black holes. Its size and relative proximity allow methods such as very long baseline interferometry to probe scales close to the event horizon. It has become a proving ground for theories of accretion jet launching and feedback. The first hints from stellar and gas dynamics have blossomed into a comprehensive research program that spans the electromagnetic spectrum and pushes the limits of observational astronomy. The task of weighing the invisible mass at the heart of M87 requires careful measurements and detailed modelling. Astronomers approach the problem by studying the motions of stars and gas in the central regions of the galaxy. Stars act as test particles responding to the gravitational potential, and by observing their velocities through spectroscopy, one can infer how much mass is required to hold them in orbit. In M87, the velocities are remarkably high, reaching hundreds of kilometers per second within a small projected distance of the nucleus. This velocity dispersion cannot be explained by the luminous stars alone. When researchers compare the observations to models that include only the mass of visible stars, the stars would not move nearly as fast. The missing mass is not seen directly, but its gravitational effect is unmistakable. Gas offers another line of evidence. Ionized gas near the core emits characteristic spectral lines, and the width and shift of these lines reveal the speeds and directions of motion. In M87, gas rotates around the nucleus, with velocities indicating a central object that is not only massive, but also confined to a region smaller than the orbit of Neptune in our own solar system. Only a black hole can match such conditions, because any cluster of ordinary stars with billions of solar masses in such a small volume would collapse under its own gravity, or shine far more brightly than what is observed. By combining stellar dynamics with gas dynamics, astronomers converge on the same conclusion: a central black hole with billions of solar masses is required. Refinements in these measurements came with the use of the Hubble Space Telescope. Its high resolution allowed the study of gas disks close to the nucleus. Observations showed a thin disk of ionized gas orbiting at high speed, tilted relative to the main body of the galaxy. By modelling the rotation curve of this disk, researchers derived a central mass of several billion solar masses. Later, with improvements in ground-based adaptive optics and large instruments such as those at the Very Large Telescope Stellar Kinematics were measured with even greater accuracy. These results consistently supported a mass estimate of around 6.5 billion solar masses for the central black hole, making it one of the most massive directly measured. The measurement process involves careful handling of uncertainties. Stellar orbits are not all aligned, and some stars move in eccentric orbits that complicate the velocity distribution. Gas can be influenced by non-gravitational forces such as pressure or turbulence, which must be accounted for in models. Nevertheless, even when these complexities are included, the mass estimate remains robust. The error margins are not small, but they are narrow enough to confirm that the central mass lies in the billions of solar masses, far beyond any alternative explanation. Another factor considered is the contribution of dark matter. Dark matter dominates the mass of galaxies at large radii, but within the inner regions where stars and gas near the nucleus are measured, the stellar component and black hole dominate. Models that include plausible dark matter halos still require a central black hole of the same order of magnitude. Thus, the evidence does not depend on assumptions about dark matter distribution. Weighing such an object is not only an achievement of observational technique, but also a test of theoretical expectations. General relativity predicts that a black hole's event horizon radius scales with its mass. For a black hole of 6.5 billion solar masses, the event horizon spans a diameter larger than the orbit of Pluto. This size is immense compared to stellar black holes, yet in astronomical terms it is still tiny relative to the galaxy. The fact that a galaxy containing hundreds of billions of stars can be influenced by a single object of this scale highlights the central role black holes play in galactic evolution. The measurement of M87's black hole also provided a benchmark for scaling relations. Astronomers have found correlations between black hole mass and properties of their host galaxies, such as the velocity dispersion of the bulge stars or the total bulge mass. These relations suggest a coevolution of black holes and galaxies. M87 fits within these correlations, though it lies at the high end. Its black hole mass relative to its stellar mass is somewhat larger than average, which may indicate a history of particularly efficient growth through accretion or mergers. An important cross-check of the mass comes from very long baseline interferometry. Although this technique does not measure mass directly, it constrains the size of the emitting region near the black hole. The compactness of the radio core in M87 confirms that the mass must be confined within a very small region. If the central mass were spread out or composed of a cluster of dark remnants, the emission would appear more extended and less stable. Instead, the radio core remains compact and consistent with the expectations of a single supermassive black hole. The dynamical evidence also rules out exotic alternatives such as a cluster of neutron stars or stellar black holes. Any such cluster with billions of solar masses would quickly collapse or evaporate. The timescales for such a cluster to remain stable are far shorter than the age of the galaxy. The only stable and physically consistent explanation is a black hole. This conclusion is strengthened by the presence of the relativistic jet, which requires the extreme conditions provided by a spinning black hole interacting with magnetic fields. The act of weighing an invisible object many millions of light-years away highlights the progress of modern astronomy. From the first hints of unusual stellar motions to the precise mass estimates derived with space telescopes and advanced modelling, the story of M87's black hole demonstrates the power of indirect evidence. The gravitational pull of the black hole is written into the motions of stars and gas, and by decoding these motions, astronomers reveal the hidden mass. Each refinement in measurement not only confirms the black hole's presence, but also improves our understanding of how such objects grow and affect their galaxies. M87 thus stands as a primary case where the invisible has been weighed with remarkable precision. The result is an object whose mass is so large that it challenges intuition, yet whose existence is confirmed through multiple and independent methods. It is the convergence of evidence from stellar dynamics, gas dynamics, and interferometric imaging that gives confidence in the measurement. With this foundation, researchers can proceed to explore the more detailed properties of the black hole, such as the structure of its event horizon, the behavior of its accretion flow, and the mechanisms that launch its jet. The concept of the event horizon is central to understanding the black hole in M87. A black hole is defined by the boundary beyond which nothing, not even light, can escape. This boundary is called the event horizon, and its size is set by the mass of the black hole. For M87, with a mass of about 6.5 billion times that of the Sun, the event horizon is enormous compared to that of stellar black holes. Calculations based on general relativity show that the radius of the event horizon is roughly 3 times the mass of the black hole in kilometers. In the case of M87, this translates into a horizon with a diameter wider than our entire solar system. Despite this size, the event horizon remains far too small to be resolved by ordinary telescopes because of the immense distance to M87. Yet its presence can be inferred through its effects on nearby matter and light. One of the most striking consequences of an event horizon is the bending of light. General relativity predicts that space-time is curved by mass, and the stronger the mass concentration, the greater the curvature. Near a black hole, light does not travel in straight lines, but follows curved paths. Some light emitted from material close to the horizon bends back around the black hole, creating a region where radiation is trapped in circular orbits. The combined effect is a shadow, a dark central region surrounded by a ring of lensed light. This is what astronomers refer to as the black hole shadow. The diameter of this shadow is slightly larger than the event horizon itself because it represents the photon sphere, where light can orbit the black hole. For M87, this shadow spans a size on the sky that is comparable to that of a grapefruit on the Moon as seen from Earth. Detecting such a small feature required a network of telescopes working together across the globe. The gravitational redshift is another consequence of the event horizon. Light climbing out of the deep gravitational well loses energy, and as a result its wavelength stretches. Radiation emitted close to the black hole appears redder to a distant observer than when it was emitted. This redshift becomes extreme near the horizon where the escape velocity reaches the speed of light. Thus, even if matter near the horizon emits radiation, by the time it reaches Earth, the signal carries the imprint of the black hole's gravity. Observations of line broadening and shifts in spectral features near the nucleus of M87 confirm that matter is moving in the relativistic regime close to the event horizon. Time dilation also occurs near the horizon. According to general relativity, time passes more slowly in strong gravitational fields. To an external observer, processes near the event horizon appear to unfold at a slower pace. Material spiraling inward seems to linger near the horizon, even though in its own frame it plunges rapidly. This effect cannot be seen directly, but is an essential part of the physics that shapes the observed emission. Variability in the light curves of M87's nucleus reflects both the dynamics of inflowing matter and the relativistic effects of strong gravity. The black hole shadow provides a way to test these predictions. General relativity makes precise predictions for the size and shape of the shadow, depending on the black hole's mass and spin. If the observed shadow matches these predictions, it strengthens confidence in the theory. In M87, the Event Horizon Telescope achieved this test, producing the first image of a black hole's shadow in 2019. The image revealed a ring of light with a dark center consistent with theoretical expectations. The size of the ring matched the predicted value for a black hole of several billion solar masses at the known distance to M87. This landmark observation confirmed both the mass estimate and the presence of an event horizon. The shape of the shadow is also informative. If general relativity holds, the shadow should be nearly circular, with only slight asymmetries caused by spin or viewing angle. The observed image of M87's black hole showed such a circular structure. This agreement placed constraints on alternative theories of gravity, many of which predict different shadow shapes. Thus, M87 has become a laboratory for testing gravity in its strongest regime. The results so far favour Einstein's theory, though uncertainties remain about the spin and orientation of the black hole. The event horizon is more than a boundary. It defines the scale of all processes near the black hole. The accretion disk, the jet launching region, and the zone of extreme magnetic fields are all measured in units relative to the horizon radius. Understanding the size of the horizon therefore sets the context for all subsequent studies. For example, the collimation of the jet occurs within a few tens of horizon radii, while the disk of inflowing gas extends outward to thousands of radii. Variability in the light curves of the nucleus often reflects orbital timescales at specific multiples of the horizon radius. Even though the event horizon itself cannot be crossed by light, its influence dominates the observable environment. Radiation produced by matter falling inward carries signatures of the horizon. The brightness asymmetry seen in the Event Horizon Telescope image with one side of the ring appearing brighter is a direct consequence of relativistic beaming. Material orbiting at near light speed on the side of the disk moving toward us emits radiation that is boosted in intensity, while material on the opposite side appears dimmer. This effect, combined with gravitational lensing, shapes the observed structure of the ring. The concept of the event horizon also raises questions about the fate of information and the ultimate nature of black holes. While these remain theoretical concerns, the observational evidence in M87 grounds the discussion in real data. The shadow, the redshift, the time dilation, and the light bending are not abstract predictions but measurable features that match observations. The event horizon of M87's black hole is thus both a physical boundary and a tool for probing the laws of physics under extreme conditions. By mapping how the event horizon shapes light and matter, astronomers can refine their models of accretion flows and jets. The shadow provides a baseline for calibrating simulations, while the ring brightness distribution offers clues to the magnetic field configuration and the orientation of the accretion disk. Future observations with improved resolution and sensitivity will sharpen this picture, allowing the study of temporal changes and polarization patterns that trace magnetic fields. All of this begins with the recognition that the event horizon sets the stage, defining the region where gravity dominates absolutely. Accretion flows form the lifeblood of a black hole system, and in M87 they reveal much about how such an object interacts with its surroundings. Accretion is the process by which gas dust and sometimes even stars fall inward toward the black hole under the influence of gravity. Yet the path inward is not straightforward. Material possesses angular momentum, and this momentum prevents it from plunging directly into the horizon. Instead, the inflowing gas settles into a disk or torus, where friction, turbulence, and magnetic stresses redistribute angular momentum, allowing matter to spiral inward gradually. In stellar black holes accreting at high rates, these disks can be thin, luminous, and radiatively efficient, shining brightly in X-rays. In M87, however, conditions are very different. The central black hole of M87 accretes at a rate far below what would be expected if it simply swallowed the surrounding hot gas at the so-called Bondi rate. The gas supply exists in abundance, with the surrounding cluster atmosphere providing a reservoir of hot plasma, yet only a small fraction of this material seems to cross into the inner accretion flow. Observations suggest that much of the gas is heated, stirred, or expelled before it can reach the event horizon. As a result, the accretion flow is radiatively inefficient. This means that although matter falls inward, only a small portion of its gravitational energy is released as radiation. The rest is carried inward as heat or ejected in outflows. Theoretical models for such flows are called advection-dominated accretion flows. In these regimes, the gas is so hot and tenuous that it cannot radiate effectively before being swallowed. Temperatures reach billions of degrees, and the particles are only weakly collisional. Ions and electrons can be at different temperatures, with the ions carrying most of the heat. Radiation comes mainly from synchrotron emission bremsstrahlung and inverse Compton scattering, but the overall luminosity remains faint compared to the potential power available. In M87, this is why the nucleus is surprisingly dim for a black hole of such enormous mass. The radiative efficiency is only a tiny fraction of what would be expected from a bright quasar accreting at near the Eddington limit. The structure of the accretion flow in M87 has been modelled extensively. At large radii, the hot gas from the cluster atmosphere settles into a quasi-spherical inflow. As it approaches the black hole, magnetic fields become important, channeling and stirring the plasma. The flow may include turbulent eddies, shocks, and outflowing winds. Some models propose that much of the gas is expelled before reaching the horizon, explaining the low observed luminosity. Others suggest that the accretion proceeds, but that most of the energy remains locked in the ions until it crosses the horizon. Either way, the inner region is dominated by a thick, hot, turbulent disk, rather than a thin, luminous one. Variability in the nucleus of M87 offers clues to the flow's structure. Observations at radio-optical and X-ray wavelengths reveal flares and changes in brightness over timescales ranging from days to years. These variations likely reflect changes in the accretion rate, magnetic reconnection events, or instabilities in the flow. Because the orbital timescale near the horizon is only a few days for a black hole of this mass variations, on such timescales trace processes occurring very close to the event horizon. Monitoring these variations allows astronomers to link theory and observation, connecting the statistical behavior of light curves to the dynamics of turbulent plasma. The spectrum of radiation from the nucleus also encodes the flow conditions. At radio wavelengths, synchrotron emission from relativistic electrons dominates. In the infrared and optical bands, a combination of synchrotron and Compton processes contributes. In X-rays, bremsstrahlung from hot gas and inverse Compton scattering of lower energy photons are important. The relative strengths of these components depend on the density, temperature, and magnetic field of the plasma. By fitting the observed spectrum with theoretical models, astronomers constrain the properties of the accretion flow. In M87, the spectrum confirms a hot, radiatively inefficient regime. An important concept in accretion physics is the Eddington limit, which sets the balance point between gravity pulling gas inward and radiation pressure pushing it outward. A black hole accreting at the Eddington rate shines with a luminosity proportional to its mass. For M87's black hole, the Eddington luminosity would be extraordinarily high, outshining entire galaxies. Yet the actual luminosity of M87's nucleus is many orders of magnitude lower than this. The black hole is therefore accreting at a tiny fraction of the Eddington rate. This contrast highlights the difference between active quasars in the distant universe and the subdued state of M87 today. The geometry of the accretion flow likely includes a magnetized torus feeding the base of the jet. Simulations using general relativistic magnetohydrodynamics show that when strong magnetic fields accumulate near a spinning black hole, they can arrest the inflow and channel material into collimated jets. In such magnetically arrested disk models, the accretion flow becomes turbulent and strongly influenced by magnetic stresses. These simulations produce variability in structures similar to what is observed in M87. They suggest that the interplay between inflow and magnetic fields is key to understanding how the jet is powered. The low radiative efficiency of M87's accretion flow means that most of the energy is not emitted as light, but is instead carried in mechanical or magnetic form. This energy powers the jet inflates cavities in the cluster gas and regulates star formation in the galaxy. Thus, the faintness of the nucleus does not imply weakness, but rather reflect how the black hole channels energy into forms other than light. The system is a reminder that accretion flows can operate in very different regimes depending on density, temperature, and magnetic field. Comparisons with other systems underline this point. In smaller black holes with higher accretion rates, thin luminous disks dominate, producing strong X-ray emission and sometimes bright optical and ultraviolet radiation. In M87, the much larger mass combined with low accretion rate creates a flow that is geometrically thick, optically thin, and radiatively inefficient. The contrast between these modes illustrates the diversity of black hole accretion and its dependence on both external supply and internal physics. By piecing together the observational evidence, astronomers conclude that the accretion flow in M87 is a hot, turbulent, magnetized plasma feeding the black hole at a low rate, but providing the conditions necessary to launch the powerful relativistic jet. The flow is not directly visible as a glowing disk, but instead reveals itself through the faint multi-wavelength emission and through its role in shaping the larger environment. This state may represent a common phase in the lives of massive black holes, particularly in the present universe where many galaxies are quiescent. Understanding M87's accretion flow therefore illuminates not only this galaxy, but also the broader cosmic population of black holes. Magnetic fields play a central role in the behavior of matter near the black hole in M87. Without magnetic fields, accretion flows would struggle to shed angular momentum, and jets would not be launched in their observed forms. In the hot plasma surrounding the black hole, atoms are stripped of their electrons, producing a soup of charged particles. This plasma interacts naturally with magnetic fields, twisting and stretching them as the particles orbit and spiral inward. In turn, the magnetic fields exert stresses and forces that influence the motion of the plasma. The result is a feedback loop in which plasma and magnetism shape one another. In an accretion disk, turbulence driven by the magnetorotational instability enables angular momentum to be transferred outward. This process allows matter to lose energy and spiral closer to the black hole. The instability arises when weak magnetic fields link different parts of the disk. Inner regions orbit faster than outer regions, and the connecting field lines stretch and amplify, enhancing turbulence. This turbulence acts like an effective viscosity, though it is not a simple friction, but a magnetically mediated process. The turbulence redistributes angular momentum and ensures that matter can move inward while energy is dissipated. Without this mechanism, accretion flows would stall, unable to bring material to the horizon. Near the event horizon, magnetic fields grow stronger. Simulations of magnetohydrodynamic flows show that the inflowing plasma can drag field lines toward the black hole, where they become compressed and intensified. In some cases, the fields accumulate to such a degree that they become dynamically dominant. This is the magnetically arrested disk state, where magnetic pressure resists further inflow and channels energy into powerful outflows. In M87, evidence suggests that the central engine operates in such a state, with strong fields threading the horizon and driving the relativistic jet. The interaction between magnetic fields and a spinning black hole is captured in theoretical models such as the Blandford-Znajek mechanism. In this framework, the rotational energy of the black hole is tapped by magnetic fields that thread the event horizon. The twisting of these fields, combined with the dragging of space-time near the horizon, launches a pointing flux-dominated jet outward at relativistic speeds. The efficiency of this process depends on the strength of the fields and the spin of the black hole. While the exact spin of M87's black hole remains uncertain, the presence of such a powerful jet suggests that either the spin is high, the magnetic flux is large, or both. Another proposed mechanism, the Blandford-Payne process, operates in the accretion disk itself. In this scenario, magnetic field lines anchored in the rotating disk fling plasma outward centrifugally, similar to beads sliding along spinning wires. If the field lines are inclined at a suitable angle, matter can be accelerated outward and collimated into a jet. In reality, both processes may operate together, with the black hole's spin and the disk's rotation contributing to the launch and collimation of the jet. Distinguishing their relative contributions is an active area of research. Observational evidence for the role of magnetic fields in M87 comes from polarization studies. Light emitted by synchrotron processes is naturally polarized, meaning its electric field oscillates preferentially in certain directions. By mapping the polarization of radiation from the nucleus, and jet astronomers can infer the orientation and structure of magnetic fields. The Event Horizon Telescope has produced polarization maps of the emission near the horizon of M87's black hole, revealing a pattern consistent with strong ordered fields. These results support the idea that magnetic fields guide the flow of plasma and shape the jet's base. On larger scales, polarization measurements of the jet also reveal ordered fields. The jet does not appear chaotic, but shows signs of helical or toroidal magnetic structures that maintain coherence across thousands of light years. Such structures help to stabilize the jet against disruption as it propagates. Without magnetic collimation, the jet would quickly disperse into the surrounding medium. Instead, it maintains its narrow shape over vast distances, a testament to the guiding influence of magnetic fields. The strength of the magnetic fields near the black hole is difficult to measure directly. Estimates come from modeling the synchrotron emission and comparing it with theoretical expectations. In M87, field strengths of tens to hundreds of Gauss are inferred near the horizon. These values are many orders of magnitude stronger than the typical interstellar magnetic fields in galaxies, which are only a few microgauss. Such intense fields are necessary to account for the energy and structure of the jet. They also explain the ability of the accretion flow to remain hot and turbulent, since magnetic reconnection events can rapidly heat particles and accelerate them to relativistic speeds. Magnetic reconnection is another crucial process. When field lines of opposite orientation come into close contact, they can rearrange and release stored magnetic energy as heat and particle acceleration. In the turbulent plasma near the black hole, reconnection is likely common. Flares and variability observed in M87's nucleus may be the signatures of such events. Electrons accelerated in reconnection regions can produce bursts of synchrotron radiation, explaining sudden brightenings in the radio or optical bands. This connection between field dynamics and observable variability ties the microscopic physics of plasma to the macroscopic behavior of the galaxy. The interplay of magnetic fields and plasma in M87 has consequences far beyond the immediate vicinity of the black hole. The energy extracted through magnetic processes powers the relativistic jet, which extends on scales of thousands of light-years. The jet in turn affects the surrounding galaxy and cluster inflating cavities in the hot gas and heating the intracluster medium. Thus, the invisible lines of force generated in the plasma near the horizon end up shaping the environment of an entire cluster of galaxies. This chain of influence underscores the importance of magnetic fields in astrophysical systems. Theoretical and computational studies continue to refine the picture. General relativistic magnetohydrodynamic simulations reproduce many observed features, including the shadow seen by the Event Horizon Telescope and the collimated jet. These simulations show how magnetic fields thread the horizon, twist into helical structures, and accelerate plasma outward. They also reveal complex turbulence and intermittent outflows that match the variability seen in real observations. By comparing simulation outputs with polarization maps, spectra, and variability data, researchers test the fidelity of their models. In M87, the agreement has been strong, reinforcing the central role of magnetic fields in the system. Ultimately, the study of magnetic fields in M87 illuminates fundamental processes in astrophysics. It shows how energy can be extracted from black holes, how plasma can be accelerated to near light speed, and how jets can remain collimated across intergalactic space. It also demonstrates that even in environments dominated by gravity, magnetism exerts a profound influence. The black hole in M87 is not merely a sink of matter, but an engine powered and shaped by magnetic interactions linking the smallest scales near the horizon to the larger scales of the galaxy cluster. Close to the event horizon of M87's black hole, the relativistic jet begins its journey outward. Jets are among the most striking features of active galaxies, and in M87 the jet has been studied for more than a century, ever since it was first seen as a narrow optical streak extending from the galaxy's core. Understanding how such a jet forms requires linking the dynamics of the accretion flow and the magnetic fields to the processes that accelerate and collimate plasma. The observations show that the jet is already collimated within a few tens of gravitational radii of the horizon. This means the shaping of the flow into a narrow beam begins almost immediately in the region, where gravity, plasma, and magnetism interact most strongly. The velocity of the jet near its base is relativistic, meaning close to the speed of light. Measurements of apparent motion within the inner jet, made using very long baseline interferometry, reveal components moving outward at several times the speed of light. These superluminal motions are an illusion caused by relativistic beaming, when objects move nearly at light speed at small angles to our line of sight. In reality, the plasma moves just below light speed, but the combination of high velocity and orientation produces the effect. The existence of such speeds demonstrates the enormous energy available in the launching region. Collimation of the jet requires magnetic fields. As plasma spirals inward through the accretion flow, magnetic field lines become twisted by rotation. The twisting creates helical fields that can guide plasma outward along the rotational axis. The structure resembles a nozzle focusing the outflow into a narrow channel. Observations of M87's jet at scales of tens to hundreds of gravitational radii show that its width decreases with distance, consistent with gradual collimation. At larger scales, the jet maintains this narrow structure for thousands of light years, a sign that magnetic fields preserve coherence across immense distances. The jet is not smooth, but contains bright knots and regions where emission intensifies. These knots represent shocks, or sites where particles are accelerated. Near the base of the jet, changes in the flow can cause shocks that energize electrons, producing bursts of synchrotron radiation. Such regions are visible across the electromagnetic spectrum from radio to X-ray. The presence of these knots indicates that the jet is dynamic, not a steady stream, but a structure where turbulence, instabilities, and magnetic reconnection continually inject energy. One of the best studied features of the M87 jet is a bright knot called HST1, located about 60 parsecs from the nucleus. This knot has exhibited dramatic variability, with flares observed in optical and X-ray bands. The brightness changes suggest rapid particle acceleration and energy release, possibly linked to shocks or reconnection events. The study of HST1 and similar features provides insight into how jets transport energy and how particles within them are accelerated to relativistic energies. Polarization measurements of the jet near its base reveal ordered magnetic fields aligned along or across the jet. This order suggests that the jet is magnetically dominated close to the black hole, with the energy carried primarily as Poynting flux, rather than as kinetic energy of matter. Farther out, the jet gradually converts this magnetic energy into kinetic energy of particles. The transition from magnetically dominated to particle-dominated flow is a central theme in jet physics, and M87 offers a rare opportunity to study it across many scales. The brightness asymmetry of the jet compared to any possible counterjet provides further clues. In M87, the visible jet points somewhat toward Earth, while the counterjet directed away is faint or invisible. Relativistic beaming explains this asymmetry. Radiation emitted by plasma moving toward us is boosted in intensity, while radiation from plasma moving away is diminished. By modeling the brightness difference, astronomers constrain the jet's velocity and orientation. The results confirm speeds close to light and a viewing angle of about 15 to 20 degrees relative to our line of sight. The inner jet has also been mapped at high resolution, using the Event Horizon Telescope and related arrays. These observations reveal a limb-brightened structure with the edges of the jet appearing brighter than the center. This pattern suggests a spine sheath configuration, where the central spine of the jet moves fastest, while a surrounding sheath of slower plasma interacts with the environment. The difference in velocity across the jet may help stabilize it and produce the observed radiation. Such structures are consistent with magnetohydrodynamic simulations, which naturally produce layered jets when magnetic fields and plasma interact. The stability of the M87 jet across immense distances is remarkable. Without collimation, a stream of plasma moving through intergalactic space would quickly disperse, yet the M87 jet retains its narrow form for thousands of light years. Magnetic fields again appear to be the key maintaining pressure and order. Helical field structures may act like tensioned wires keeping the plasma confined. Observations of polarization across the jet support the presence of such helical fields. This stability allows the jet to deliver energy far from the black hole, influencing the surrounding galaxy and cluster gas. The origin of variability in the jet remains an active topic. Rapid flares seen in X-rays and gamma rays suggest that particles are accelerated to extreme energies close to the black hole. These flares may result from magnetic reconnection events, shocks in the flow, or turbulence in the magnetized plasma. The timescales of these flares, sometimes only days or weeks, imply that they originate within only a few tens of gravitational radii. By monitoring these events, astronomers test theories of particle acceleration under extreme conditions. The energy carried by the jet is immense. Estimates place the power of the M87 jet at around 10 to the 44th to 10 to the 45th ergs per second, comparable to the total luminosity of an entire galaxy of stars. Yet the nucleus of M87 appears relatively faint in light, meaning most of the energy is not radiated but transported mechanically by the jet. This contrast underscores the efficiency of black holes at channeling gravitational and rotational energy into directed outflows rather than isotropic radiation. As the jet emerges from the black hole environment, it sets the stage for its long journey across the galaxy and beyond. The near-horizon region is the cradle of this enormous structure, where plasma magnetism and gravity converge to produce one of the most powerful phenomena in astrophysics. M87 provides the clearest view of such processes, offering a direct link between theory, simulation, and observation. The relativistic jet, seen so vividly across the electromagnetic spectrum, stands as the visible signature of the hidden forces at work near the event horizon. On scales far larger than the immediate horizon, the jet of M87 reveals itself as one of the most extended and studied structures in extragalactic astronomy. Stretching thousands of light years, it cuts across the galaxy and continues into intergalactic space, visible in multiple wavelengths from radio to X-ray. Even though the black hole lies tens of millions of light years away, the jet is bright enough that it can be imaged in optical light with modest telescopes, an extraordinary fact that highlights its power. Early observers saw it as a linear streak, but modern instruments show a complex and evolving structure composed of knots, filaments, and shocks that trace the flow of energy outward from the central engine. Radio observations provide the clearest large-scale maps of the jet. At these wavelengths, synchrotron emission from relativistic electrons dominates, producing bright lobes at the ends of the outflow where it terminates in the surrounding medium. The radio lobes of M87 extend tens of thousands of light years and appear as inflated bubbles of plasma. Within them, electrons spiral around magnetic field lines radiating over millions of years. These lobes mark the long-term influence of the jet on the environment, showing where energy carried outward is finally deposited. They also reveal how the jet interacts with the intracluster medium, displacing hot gas and creating cavities observed in X-rays. Optical images from the Hubble Space Telescope reveal the jet in exquisite detail. Bright knots are seen along its length, each representing a site of particle acceleration. These knots often show superluminal motion, with apparent speeds faster than light caused by relativistic projection effects. By tracking these knots over time, astronomers reconstruct the velocity and dynamics of the flow. The optical emission again comes from synchrotron radiation, which requires continual acceleration of electrons since otherwise they would lose energy too quickly to account for the brightness. This means that the jet is not simply a stream of plasma launched once and left to coast, but a dynamic structure with ongoing energy input along its path. X-ray observations add another layer. With the Chandra X-ray Observatory, astronomers see knots along the jet glowing in high-energy radiation. The X-ray emission can be explained either by synchrotron radiation from ultra-relativistic electrons or by inverse Compton scattering, where lower-energy photons are boosted to X-ray energies by collisions with fast electrons. Distinguishing between these mechanisms is not straightforward, and different knots may be dominated by different processes. The presence of X-ray emission confirms that the jet accelerates particles to energies far beyond what is achieved in human laboratories. The large-scale morphology of the jet reveals bending and broadening as it travels outward. Although it begins narrow near the core, it gradually widens with distance, interacting with the interstellar and intracluster medium. At some points, instabilities appear to develop, creating wiggles or oscillations in the jet's path. These features are consistent with fluid and magnetic instabilities that naturally arise in such flows. Despite these instabilities, The jet remains coherent over enormous scales, a testament to the stabilizing influence of magnetic fields and relativistic speeds. The termination of the jet produces shocks, where the outflow collides with surrounding gas. These shocks accelerate particles and create bright hotspots visible in radio and X-ray bands. The energy deposited in these regions inflates the radio lobes and drives turbulence in the intracluster medium. In this way, the jet of M87 connects the smallest scales near the black hole to the largest scales of the cluster environment, transferring energy across a range spanning many orders of magnitude. Studies of the jet across multiple wavelengths have led to a model in which different energy ranges trace different populations of particles and different regions of the flow. Radio emission arises from older, less energetic electrons distributed throughout the lobes. Optical and X-ray emission arise from more recently accelerated particles in localized knots. Gamma-ray observations, though less resolved, suggest that the jet produces even higher energy radiation, possibly through inverse Compton scattering or hadronic processes involving protons. M87 has been detected in very high energy gamma rays, confirming that it accelerates particles to extreme energies. The site of this gamma ray emission remains debated, with candidates ranging from the innermost jet to knots like HST-1. The orientation of the jet relative to Earth makes it an especially valuable target. It is not pointed directly at us as in blazars, but instead is viewed at a modest angle. This allows us to see the structure along its length, rather than being blinded by beamed emission from the core. As a result, M87 provides a more complete view of jet physics across scales. We can trace how plasma evolves from the launching region near the black hole, through the collimation zone, and into the extended lobes. Few other systems offer such a comprehensive picture. The impact of the jet on the host galaxy and cluster is profound. The lobes displace hot gas, producing cavities that rise buoyantly like bubbles in water. These cavities are seen in X-ray images as depressions in the diffuse emission around M87. As they rise, they transport energy and stir turbulence in the intracluster medium. This heating counteracts the cooling of the gas, preventing it from condensing into stars at the rates expected. Thus the jet regulates star formation, not only in M87 but also in the central region of the Virgo Cluster. This feedback process is a central theme in galaxy evolution, showing how black holes can control the growth of their hosts. The timescales involved are immense. Radio lobes persist for tens of millions of years long after individual knots have flared and faded. By studying the sizes and shapes of the lobes, astronomers infer the duty cycle of jet activity, concluding that the black hole in M87 has been launching jets intermittently for hundreds of millions of years. The cavity and ripples in the X-ray gas act as records of past outbursts, much like tree rings, record the history of growth. In this way, M87 provides not only a snapshot of jet physics today, but also a historical record of black hole activity over cosmic time. Despite the progress, open questions remain. How exactly does the jet maintain stability against instabilities over such scales? How is energy partitioned between magnetic fields, electrons and protons? What determines the sites of particle acceleration along the jet? These questions drive ongoing observations and simulations. M87 remains the benchmark system for testing answers, combining proximity, brightness, and scale in a way no other active galaxy does. Its jet stretching from near the horizon of the black hole to the outskirts of the cluster continues to illuminate fundamental physics of plasma magnetism and gravity. Radiation from the jet of M87 covers a vast span of the electromagnetic spectrum, and understanding the mechanisms that produce this radiation is essential for interpreting what is seen. The dominant process across radio-optical and even X-ray bands is synchrotron emission. In this process, relativistic electrons spiral around magnetic field lines, emitting radiation that is strongly polarized and spans a broad range of frequencies. The intensity and spectrum of synchrotron emission depend on the strength of the magnetic field and the energy distribution of the electrons. In M87, synchrotron radiation explains the brightness of the jet in radio and optical images, as well as the polarization patterns that trace the underlying magnetic fields. At radio wavelengths, synchrotron emission comes from electrons with relatively lower energies that persist for long time scales. This is why the radio lobes of M87 remain bright, even though they contain particles accelerated millions of years ago. At optical and X-ray wavelengths, synchrotron emission requires much higher energy electrons which lose energy quickly. This means that the emission at these bands must be generated locally and recently, implying that particle acceleration is ongoing along the jet. Bright knots observed in optical and X-ray bands are the sites of this acceleration. The mechanisms for energizing electrons to such levels include shocks, turbulence, and magnetic reconnection, all of which are expected in a dynamic magnetized flow. Inverse Compton scattering provides another pathway to produce high-energy radiation. In this process, relativistic electrons collide with lower-energy photons and transfer part of their energy, boosting the photons to higher frequencies. In M87, possible sources of seed photons include the synchrotron radiation itself, starlight from the galaxy, and the cosmic microwave background. When electrons in the jet upscatter these photons, the result can be X-ray or gamma-ray emission. Distinguishing synchrotron from inverse Compton in observations requires careful spectral analysis, since both can produce overlapping signals. In some knots of the M87 jet, synchrotron appears dominant, while in others inverse Compton may play a role. The highest energy radiation from M87 comes in the form of gamma rays. Observatories on Earth and in space have detected M87 at very high energies up to tera-electron volts. The origin of these photons is debated. One possibility is that electrons in the inner jet upscatter photons to gamma-ray energies. Another possibility involves hadronic processes where protons are accelerated to high energies and then collide with photons or other particles, producing cascades of gamma rays. Both scenarios require efficient particle acceleration near the black hole or in bright knots along the jet. The variability of the gamma-ray emission, sometimes on timescales of days, suggests that at least part of it comes from the innermost jet rather than from distant lobes. The radiation mechanisms also reveal the composition of the jet. If electrons dominate, then synchrotron and inverse Compton processes explain the observations. If protons play a significant role, then hadronic models are needed. Evidence from polarization spectra and variability favors electron-dominated emission, but protons may still carry a large fraction of the jet's energy without radiating efficiently. This energy could manifest instead in cosmic rays, which are charged particles detected at Earth, with energies that may originate in jets like that of M87. Thus, the radiation we see is only part of the story, with much energy possibly hidden in non-radiating components. The study of radiation mechanisms in M87 links directly to the physics of particle acceleration. For electrons to emit synchrotron radiation in the optical or X-ray bands, they must be accelerated to Lorentz factors of thousands to millions. Such acceleration is possible in shocks where plasma flows collide, compress and energize particles. It is also possible in regions of magnetic reconnection, where tangled field lines snap and release energy. Observations of rapid variability in some knots indicate that such processes are efficient and localized. The connection between theory simulation and observation is particularly strong in M87, where data at many wavelengths constrain the models. The spectrum of M87's nucleus provides additional insight. At low frequencies, self-absorbed synchrotron emission dominates, producing a flat or inverted spectrum. At higher frequencies, the emission turns over and declines, indicating energy losses of the radiating particles. X-ray observations of the core show a component consistent with synchrotron emission from the innermost regions of the jet. Gamma rays add further complexity, with variability suggesting compact emission zones. Together, these data suggest a stratified structure in which different zones and processes contribute at different frequencies. Polarization of the radiation offers another diagnostic. Synchrotron radiation is intrinsically polarized, and the degree and orientation of polarization depend on the order of the magnetic field. In M87, both the jet and the near-horizon emission show significant polarization, indicating organized magnetic fields. The polarization fraction and angle change across the jet tracing helical or toroidal field geometries. Polarization variability also provides clues to changes in magnetic structure during flares. These observations confirm that magnetism is not only important for jet launching, but also for shaping the radiation we detect. The efficiency of radiation is a key parameter. In M87, despite the enormous jet power, the radiative output is only a fraction of the total. Most of the energy is transported mechanically in the bulk flow of plasma and magnetic fields. Radiation provides a tracer of the processes at work, but does not capture the full energy budget. By comparing the luminosity of the jet with estimates of cavity power in the intra-cluster medium, astronomers find that the mechanical output is far greater than the radiative one. This mismatch emphasizes the importance of studying both radiation and environmental effects to understand the jet's full impact. The diversity of radiation mechanisms in M87 makes it a natural laboratory for high-energy astrophysics. From radiosynchrotron in ancient lobes to tera-electron-volt gamma rays in the innermost jet, the galaxy showcases nearly every known emission process. Each mechanism highlights different aspects of plasma physics, magnetic fields, and particle acceleration. By combining these threads, researchers gain a comprehensive picture of how black holes channel gravitational energy into radiation across the cosmos. M87's role in this field is unparalleled because of its proximity and brightness. While many quasars and blazars exhibit similar processes, they lie much farther away, and often align directly with our line of sight, making it difficult to disentangle structure. M87 offers a side view of a nearby massive system, where emission regions can be resolved and tracked. The lessons learned from its radiation mechanisms apply broadly to black holes and jets throughout the universe. They also connect astrophysics with particle physics, since the energies involved rival or exceed those produced in human accelerators. By continuing to study the radiation across all bands, astronomers refine models of jet composition, particle acceleration, and magnetic structure. Observations with new telescopes promise greater sensitivity and resolution, allowing the mapping of polarization variability and spectra with unprecedented detail. The jet of M87 glowing across the spectrum remains a cornerstone in the quest to understand how matter, magnetism, and gravity combine to produce the most powerful engines in the universe. The effort to directly observe the region around the black hole in M87 culminated in the work of the Event Horizon Telescope, a global collaboration that used very long baseline interferometry to achieve resolution finer than any single telescope could obtain. The principle of very long baseline interferometry is to link radio dishes spread across the Earth, synchronizing them with atomic clocks so that their signals can be combined as if they came from a single instrument with a diameter equal to the separation between the farthest dishes. By doing this at millimeter wavelengths, astronomers achieved angular resolution capable of resolving features as small as tens of microarc seconds, just enough to image the shadow of the black hole in M87. In 2017, an international array of telescopes, including facilities in North America, South America, Europe, Hawaii, and the South Pole, joined forces to observe M87. The data was so extensive and complex that they required months of processing. When the results were announced in April 2019, they showed the first image ever captured of a black hole's shadow. The image displayed a bright ring of emission encircling a dark central region. The size of the ring matched predictions from general relativity for a black hole with a mass of several billion suns at the known distance of M87. The dark interior represented the shadow the region where light paths are bent inward by gravity and fail to reach Earth. This achievement confirmed decades of theoretical work. General relativity had predicted that a black hole would produce such a shadow, nearly circular in shape with slight asymmetry, due to the black hole's spin and the orientation of the accretion flow. The observed ring was consistent with these predictions, providing one of the most direct tests yet of the theory in the regime of strong gravity. The measurement also offered an independent way to weigh the black hole. The diameter of the shadow depends directly on the mass, and the observed value agreed with dynamical estimates based on stars and gas. This convergence of independent methods gave confidence that the mass of about 6.5 billion solar masses is correct. The brightness of the ring was not uniform. One side appeared brighter than the other. This asymmetry arises from relativistic beaming. Material in the accretion flow or inner jet moves at relativistic speeds. Radiation emitted in the direction of motion is boosted in intensity, while radiation emitted in the opposite direction is diminished. Because the disk is rotating, one side is moving toward us and the other away. The result is a bright crescent rather than a perfectly uniform ring. This feature matched predictions from simulations confirming that the image captures the effects of both gravity and relativistic motion. Producing the image required overcoming immense technical challenges. The data recorded by each telescope filled hundreds of hard drives, which were physically transported to central facilities of correlation. Atmospheric fluctuations, instrumental noise, and synchronization errors had to be carefully corrected. Multiple teams used different algorithms to reconstruct the image independently, ensuring that the result was not an artifact of processing. The agreement between teams provided confidence that the ring was a real astronomical feature. The result was hailed worldwide as a scientific milestone, the first direct view of a black hole's immediate environment. The Event Horizon Telescope continues to improve. In subsequent campaigns, more telescopes have joined the network, increasing its sensitivity and resolution. Observations at shorter wavelengths promise even finer detail, while longer monitoring periods allow the study of temporal changes. The ultimate goal is not only to image the shadow, but also to capture movies of the dynamic accretion flow and jet base. Variability seen on timescales of days suggests that structures evolve rapidly near the horizon, and future imaging may reveal these changes directly. The significance of imaging 87's black hole extends beyond confirming theory. It opens a new window into accretion physics and jet launching. The morphology of the ring and the brightness distribution constrain the geometry of the accretion flow, the orientation of the black hole's spin, and the structure of magnetic fields. By comparing observed images with general relativistic magnetohydrodynamic simulations, researchers refine models of how plasma behaves in extreme gravity. This synergy between observation and theory represents a new era in black hole astrophysics. The image also provided an opportunity to test alternative theories of gravity. Some proposals modify general relativity and strong fields predicting different shadow sizes or shapes. The near-circular ring in M87 ruled out many such alternatives. While uncertainties remain, the results strongly support Einstein's theory. Additional observations, especially of Sagittarius A at the center of the Milky Way, provide complementary tests. Together, these cases establish the study of black hole shadows as a frontier in fundamental physics. Another layer of insight came from polarization imaging. In 2021, the Event Horizon Telescope released maps of the polarized light from M87's black hole. These maps revealed patterns that trace the magnetic field structure near the horizon. The polarization vectors showed a swirling pattern consistent with strong ordered fields threading the accretion flow. This confirmed that magnetic fields not only influence the plasma, but also shape the emission we observe. The results supported models in which magnetism plays a decisive role in launching and collimating the jet. The accomplishment of the Event Horizon Telescope highlights the power of international collaboration. No single telescope could achieve the required resolution, but by uniting facilities across continents, scientists created an Earth-sized virtual telescope. The project involved hundreds of researchers, engineers, and data analysts demonstrating the scale of effort needed to tackle such a challenge. The success of the project ensures that similar approaches will be applied to other black holes and compact objects, expanding the reach of this new technique. For M87, the Event Horizon Telescope has transformed the black hole from an abstract concept to an object with a visible silhouette. The shadow is not only a confirmation of theory, but also a starting point for detailed studies of black hole environments. Each subsequent observation adds new layers from polarization to time variability, offering a progressively sharper picture of how matter behaves under extreme conditions. M87 thus continues to stand at the center of black hole science, providing the clearest window yet into one of nature's most extreme phenomena. Polarization studies of the radiation from M87's black hole add a dimension that goes beyond simple imaging. While ordinary intensity maps show where light is emitted, polarization maps reveal the orientation of electromagnetic waves, which in turn trace the magnetic fields in the emitting region. Since synchrotron radiation dominates in the plasma near the black hole, the emitted light carries information about the geometry and strength of the magnetic fields. By observing the polarization patterns at millimeter wavelengths, astronomers can probe the role of magnetism in shaping the accretion flow and launching the jet. When the Event Horizon Telescope released its polarization images of M87 in 2021, they showed a ring similar in size to the original shadow image, but overlaid with polarization vectors forming organized patterns. These patterns were not random. Instead, they curved smoothly around the ring, suggesting that magnetic fields near the event horizon are coherent and ordered rather than chaotic. This order supports theoretical models in which magnetic fields are anchored in the accretion flow and twisted by rotation, forming structures that channel plasma outward. The polarized emission revealed a swirling geometry consistent with a magnetically dominated environment. The degree of polarization is another important diagnostic. Light can be polarized by a few percent if fields are tangled and disordered, or by tens of percent if fields are coherent. In M87, the polarization fraction was modest, but significant, implying a balance between ordered large-scale fields and turbulent small-scale structures. This result suggests that while turbulence is present in the hot accretion flow, a global magnetic structure persists, guiding the plasma and shaping the jet. The combination of order and turbulence matches expectations from magnetohydrodynamic simulations. Polarization also provides a way to estimate magnetic field strength. By modeling how electrons emit synchrotron radiation in given field configurations, astronomers infer that the fields near the event horizon of M87 reach tens to hundreds of Gauss. These values are sufficient to influence plasma dynamics strongly and to launch a relativistic jet. They also indicate that the black hole may operate in a magnetically arrested state, where inflowing plasma brings in so much magnetic flux that the fields accumulate and dominate the dynamics. Such a state can tap efficiently into the rotational energy of the black hole, consistent with the enormous power of M87's jet. Farther along, the jet polarization continues to offer clues. Optical and radio observations of the kiloparsec scale jet show that the radiation is also polarized with orientations that reveal helical or toroidal magnetic field structures. These fields help to maintain collimation of the jet as it travels thousands of light years. The persistence of polarization over such scales demonstrates that magnetic order extends far beyond the immediate vicinity of the black hole. The continuity between near-horizon fields and large-scale fields suggests that the jet retains its magnetic backbone across immense distances. Changes in polarization with time reveal dynamic processes. In some regions of the jet, polarization angles swing during flares, indicating that magnetic reconnection, or shocks, are altering the field structure. These swings correspond to sudden bursts of radiation at multiple wavelengths, confirming that magnetic activity drives variability. In the core, polarization variability on timescales of days hints at changes very close to the event horizon. Such rapid changes are consistent with turbulence in the accretion flow or transient reconnection events in the magnetized plasma. Another tool is Faraday rotation, the twisting of polarization angles, as light passes through magnetized plasma. By measuring how polarization changes with wavelength, astronomers determine the density and magnetic field of intervening material. In M87, Faraday rotation measurements suggest that the plasma around the black hole is hot and tenuous, with magnetic fields aligned along the jet. These measurements refine models of the accretion flow, confirming that it is radiatively inefficient and magnetically influenced. Comparisons with theoretical simulations reinforce these interpretations. General relativistic magnetohydrodynamic models predict polarization structures that can be compared directly with the Event Horizon Telescope maps. Simulations with strong-ordered fields produce polarization patterns similar to what was observed, while simulations with weak or chaotic fields do not. This agreement strengthens the case that magnetic fields play a decisive role in launching the jet of M87. It also provides a way to constrain the spin and orientation of the black hole, since these parameters affect the magnetic configuration. Polarization studies bridge the gap between small and large scales. Near the horizon, polarization reveals ordered fields that thread the accretion flow. Along the jet, polarization shows how those fields remain coherent, guiding plasma over kiloparsecs. In the lobes, polarization maps trace fields tangled by turbulence, showing how energy is finally dissipated. Each stage of the jet's journey carries magnetic signatures, and polarization is the key to decoding them. Without polarization, we would see only intensity maps. With it, we gain a window into the invisible architecture of magnetism. The significance of polarization extends beyond M87. By applying similar techniques to other black holes, astronomers test whether magnetically dominated flows are universal, or whether M87 is special. Early results suggest that strong fields are common, but only in M87 have we mapped them with such detail. This makes M87 not just a case study, but a benchmark for the role of magnetic fields in black hole systems. Its polarization maps stand as the most direct evidence yet that magnetic fields shape both the immediate environment of a black hole and the largest outflows in the universe. Polarization also connects observational astronomy with plasma physics. Processes such as magnetic reconnection, turbulence, and particle acceleration are well studied in laboratory and solar contexts, but in M87 they occur under conditions of extreme gravity and relativistic speeds. By observing how polarization changes during flares or across structures, scientists test whether the same physics applies. M87 thus links the microphysics of plasma to the macrophysics of galaxies and clusters. In the future, polarization studies will expand with more sensitive arrays and higher resolution. Additional telescopes in the Event Horizon Telescope network will sharpen the polarization maps, while multi-wavelength campaigns will trace polarization from radio to X-ray. These efforts will allow researchers to follow magnetic fields from the event horizon to the outer lobes, building a continuous picture. The hope is to see not only static patterns, but also dynamic evolution watching, as fields twist, reconnect, and accelerate particles in real time. M87's polarization results already provide a coherent story. They show that ordered magnetic fields exist near the horizon, that these fields collimate the jet, that turbulence modulates the flow, and that reconnection powers variability. They confirm theoretical expectations while offering new puzzles about the balance of order and chaos in magnetized plasma. Above all, they demonstrate that the invisible magnetic skeleton of the black hole environment can be revealed through careful study of light's polarization. The influence of the black hole in M87 is not confined to the immediate region of the accretion flow or the jet, but extends outward into the galaxy and the cluster environment. Astronomers refer to this as feedback, the process by which energy released near the horizon propagates to much larger scales and regulates the behavior of gas and stars. In M87, feedback is visible in the form of cavities, ripples, and shocks in the hot intracluster medium. These features show that the black hole has injected vast amounts of energy into its surroundings over millions of years. X-ray observations with the Chandra Observatory provide the clearest view of this feedback. The hot gas that fills the Virgo cluster glows in X-rays, and images reveal depressions or cavities in this emission centered around M87. These cavities correspond to bubbles filled with relativistic plasma from the jet. As the jet pushes outward, it inflates these bubbles, displacing the surrounding hot gas. The cavities rise buoyantly, much like bubbles in a liquid, and transport energy away from the nucleus. Their sizes and locations record the history of jet activity. Some cavities are tens of thousands of light-years across, requiring enormous energy to inflate. Ripples in the X-ray gas provide further evidence. Concentric arcs around M87 mark weak shocks or sound waves, driven by episodic outbursts from the black hole. These ripples carry energy through the cluster medium, heating the gas as they propagate. The energy input is enough to offset the cooling of the gas, preventing it from condensing into stars at the rates expected. Without this heating, the central regions of the Virgo cluster would experience a cooling flow in which gas radiates, energy cools, and sinks toward the center, forming stars at levels far above what is observed. The fact that star formation is suppressed indicates that feedback from the black hole is effective. The balance between cooling and heating is delicate. Gas in the cluster radiates energy, continuously trying to cool. The black hole, through its jets and outflows, supplies energy intermittently, reheating the gas. If the black hole injects too little energy, the gas would cool and form stars. If it injects too much, the gas would be overheated and dispersed. Observations suggest that in M87, the feedback cycle achieves a rough balance, maintaining the hot atmosphere in a quasi-steady state. This self-regulation may be a common mechanism in galaxy clusters, ensuring that black holes and their host galaxies evolve together. Feedback also influences the chemical composition of the gas. Jets stir the medium-mixing metals produced by supernovae throughout the cluster core. Observations of X-ray spectra reveal distributions of iron and other elements that match models of enrichment through feedback. The black hole, therefore, not only regulates star formation, but also redistributes the products of stellar evolution, influencing the cluster's chemical history. The energy budget of feedback can be estimated by measuring the volume of cavities and the pressure of the surrounding gas. The product of these values gives the work done to inflate the cavities. For M87, the inferred energies are on the order of 10 to the 57th ergs, comparable to the output of millions of supernovae. Such energy injection over millions of years demonstrates the enormous power of the black hole even when its radiative output is modest. The mechanical energy carried by the jet dominates the overall impact on the environment. On optical scales, feedback manifests in filaments of cooler gas extending outward from the nucleus. These filaments seen in hydrogen emission lines are thought to be lifted and stretched by rising bubbles. They show that the interaction between hot and cool phases of gas is complex, with feedback influencing multiple components of the interstellar and intracluster medium. Some filaments may eventually fall back, providing fuel for further accretion, linking the feedback cycle with the feeding of the black hole. The suppression of star formation in M87 itself illustrates the importance of feedback. Despite its enormous mass and gas reservoir, M87 forms few new stars today. The old stellar population dominates with little evidence of recent bursts. Models predict that without feedback, the gas cooling from the cluster atmosphere would produce thousands of solar masses of new stars each year. Instead, observed rates are far lower, consistent with the energy injection seen in X-rays. The black hole has effectively quenched star formation, locking M87 into its present quiescent state. Feedback also shapes the dynamics of the cluster. Cavities and shocks stir turbulence, driving motions in the hot gas that can be measured through Doppler shifts in X-ray spectra. These motions transport energy and mix material across the cluster core. The velocity structure of the gas confirms that feedback maintains turbulence at levels sufficient to distribute heat, but not so high as to disrupt the cluster's overall equilibrium. In this way, the black hole acts as a regulator, not only of its host galaxy, but of the cluster environment itself. Comparisons with other clusters show that M87 is not unique. Similar cavities and ripples are seen in systems like the Perseus cluster. The lessons from M87 therefore extend to a broader class of galaxy clusters, demonstrating a universal role for black hole feedback. The proximity of M87, however, allows much finer detail to be studied, making it the benchmark case. The long-term impact of feedback is profound. Over billions of years, repeated outbursts from the black hole have limited the growth of M87 by preventing excessive star formation. They have also influenced the evolution of the Virgo cluster by heating and stirring its gas. The black hole, though occupying a region smaller than our solar system, exerts control over a system spanning millions of light years. This disparity in scale highlights the extraordinary leverage of feedback. Future observations aim to measure feedback more precisely. High-resolution X-ray spectroscopy will map gas motions in detail, while improved radio imaging will trace the history of jet activity. Simulations combining magnetohydrodynamics and cosmology seek to reproduce the cycle of accretion, outburst, and feedback. M87 remains central to these efforts, providing the best laboratory for connecting black hole physics with galaxy and cluster evolution. The growth of the black hole in M87 has been a subject of sustained investigation, for its present mass of about 6.5 billion solar masses requires an extended history of accretion and mergers. Astronomers consider several pathways to explain such a massive object. One possibility is that it grew steadily over cosmic time by accreting gas from the surrounding galaxy and cluster environment. Another is that it experienced rapid growth in the early universe, when gas was more abundant, followed by a quieter phase, in which mergers of galaxies contributed additional mass. Both routes may have played roles, and observations offer clues to which dominated at different epochs. The stellar population of M87 indicates that the galaxy assembled early, with most stars forming more than 10 billion years ago. During that period, large inflows of gas would have been available to feed the central black hole. Simulations of galaxy formation suggest that massive halos like M87's underwent repeated mergers during this era, triggering bursts of star formation and accretion. In such mergers, the central black holes of the progenitor galaxies would sink to the center and eventually coalesce, adding their masses together. Over time, a sequence of such mergers could build a supermassive black hole of the observed scale. Evidence for past mergers is preserved in the structure of M87's halo. Streams of stars and the enormous population of globular clusters hint at a violent assembly history. The outer halo, extending hundreds of thousands of light-years, is likely the result of accreted satellites. Each merger would have delivered not only stars but also gas and a central black hole. The coalescence of these black holes would have contributed to the growth of the present object. Gravitational wave signals from such mergers are expected, though at frequencies detectable only by future space-based observatories. M87 thus represents a target for gravitational wave astronomy, potentially confirming the merger-driven growth scenario. Accretion remains another pathway. Gas from the cluster atmosphere is available, though in the present epoch only a small fraction reaches the horizon. In the past, accretion rates may have been much higher. During phases of rapid inflow, the black hole could have shone as a luminous quasar, releasing vast amounts of radiation. Today it is subdued, accreting inefficiently, but the history of its growth likely includes brighter phases. Feedback processes that regulate star formation also regulate accretion, linking the growth of the black hole with the evolution of the galaxy. The spin of the black hole offers a potential clue to its history. Black holes gain spin when material with angular momentum falls in, and they can also have their spin altered by mergers. A black hole fed steadily from a disk aligned with its spin axis may reach high spin, while a black hole that grows through many random mergers may end with moderate or low spin. Measuring the spin of M87's black hole is difficult, since it requires interpreting emission features and jet dynamics in the context of theoretical models. Estimates vary, with some suggesting a high spin to power the strong jet, and others allowing lower spin if magnetic fields are especially strong. The uncertainty reflects the complexity of disentangling spin effects from magnetic and plasma effects. The orientation of the jet also carries information. If the spin axis of the black hole aligns with a large-scale jet, then the spin has likely remained stable for long periods. Observations of M87 show a remarkably straight jet extending for thousands of light-years, implying that the spin axis has not wandered significantly. This stability suggests that either the black hole has maintained a consistent feeding orientation, or that magnetic fields have aligned the system. The lack of strong precession in the jet argues against frequent recent mergers with misaligned black holes, though such events could still have occurred in the distant past. Another aspect of a growth is the rate at which the black hole consumes stars. In dense stellar environments, stars can be perturbed onto orbits that lead them close to the horizon, where they are tidally disrupted and accreted. While such events are rare in M87 today over billions of years, they could contribute modestly to growth. However, this process is minor compared to accretion of gas and mergers. Still, occasional tidal disruption events may occur, and their signatures would provide unique insights into the dynamics of the core. Numerical simulations of black hole growth within clusters suggest that the central object can dominate the mass distribution early on. Once it reaches a threshold of billions of solar masses, it becomes less dependent on accretion and more on mergers for further growth. M87's black hole likely crossed that threshold long ago, making mergers the dominant growth mode in later epochs. The large mass and extended halo of M87 support this view, consistent with it being the product of many mergers. The growth history of M87's black hole is connected with the regulation of the galaxy's star formation. During phases of rapid accretion, radiation and outflows would have heated and expelled gas-suppressing star formation. This feedback established the present-day quiescent state where little new star formation occurs. Thus, the very process that built the black hole also set the conditions for the stellar population of the galaxy. The co-evolution of black holes and galaxies is visible in M87 with its massive black hole and old stars testifying to a shared history of early formation, followed by long-term regulation. Open questions remain about the details of this history. Was M87's black hole ever a luminous quasar visible across the universe? How many mergers contributed to its present mass, and what were their properties? What is the current spin, and does it reflect steady accretion or chaotic growth? Future observations may answer these questions. Gravitational wave detectors in space will detect mergers of supermassive black holes, providing direct evidence for the merger pathway. High-resolution imaging and spectral studies may constrain spin more tightly. Together, these advances will fill in the picture of how M87's black hole became the giant we see today. M87 thus embodies the story of growth through cosmic time. Its black hole is not merely an isolated monster, but the product of billions of years of feeding and merging intertwined with the fate of its galaxy and cluster. Each star stream, each globular cluster, each cavity in the gas tells part of the story. The central mass, though unseen directly, is the record of this history written in gravity. The methods used to study M87 and its central black hole illustrate the full range of observational astronomy, from radio interferometry to X-ray spectroscopy, each technique probing different aspects of the system. Very long baseline interferometry provides the sharpest resolution by linking telescopes across Earth, allowing the Event Horizon Telescope to produce images of the black hole shadow. This method depends on measuring the interference of radio waves collected at widely separated sites with timing precision provided by atomic clocks. The result is angular resolution finer than any individual telescope could achieve, enough to resolve structures only a few light days across in a galaxy tens of millions of light-years away. The success of this method rests on international cooperation and advanced data processing, highlighting how technical ingenuity expands the frontiers of observation. Spectroscopy is another critical tool. By splitting light into its component wavelengths, astronomers measure Doppler shifts that reveal velocities of stars and gas. In M87, spectroscopy of stars near the nucleus provided the earliest evidence for a massive central object, while spectroscopy of ionized gas in the inner disk confirmed rapid rotation consistent with a black hole. Emission lines also trace conditions of temperature density and ionization, giving insight into the physical state of the plasma. At larger scales, spectroscopy of X-ray emission from the hot intracluster medium reveals motions, turbulence, and chemical composition, all of which are influenced by feedback from the jet. Photometry, the measurement of brightness variations, contributes as well. Monitoring the nucleus of M87 reveals variability across multiple wavelengths, with flares and dips that trace changes in the accretion flow or magnetic field structure. The timescales of these variations, sometimes as short as days, indicate that the emission arises close to the event horizon. Photometric campaigns coordinated across the globe allow simultaneous tracking of the source in radio-optical X-ray and gamma-ray bands, providing a comprehensive view of the dynamics. Imaging across wavelengths complements these techniques. Optical images from the Hubble Space Telescope capture the jet and its bright knots in fine detail, while radio images from the Very Large Array map the extended lobes inflated by the jet over millions of years. X-ray imaging with Chandra shows cavities, ripples, and shocks in the hot gas of the Virgo Cluster, direct evidence of feedback. Each wavelength highlights a different component, from cold gas filaments in optical to hot plasma in X-ray, building a multi-phase picture of the environment. Timing studies, especially of gamma rays, reveal rapid changes that constrain emission regions. The detection of very high-energy gamma rays from M87 indicates acceleration of particles to extreme energies, but the variability of this emission on day timescales suggests that it originates near the black hole rather than in the distant jet. Such constraints help distinguish between models of emission mechanisms testing whether inverse Compton scattering or hadronic processes dominate. Polarimetry. The measurement of light's polarization adds yet another dimension. By mapping the orientation and degree of polarization, astronomers infer magnetic field structures near the black hole and along the jet. The event horizon, telescope's polarization maps confirmed ordered fields near the horizon, while optical and radio polarization trace helical structures along the kiloparsec jet. Without polarization, the magnetic skeleton of the system would remain invisible. With it, the role of magnetism becomes clear, linking the small scales of accretion to the large scales of feedback. Despite the successes, each method has limitations. Very long baseline interferometry requires bright radio emission and dense networks of telescopes, limiting the number of accessible targets. Spectroscopy depends on resolving power and signal-to-noise, which become challenging at large distances or in faint systems. Photometry and timing can reveal variability, but not always its physical cause. Imaging at different wavelengths depends on instrument sensitivity and resolution, and no single telescope can cover the entire spectrum. Polarimetry requires careful calibration, as instrumental effects can mimic or obscure real signals. Recognizing these limitations is essential to interpreting the data correctly. Systematic uncertainties also play a role. Measuring stellar velocities depends on assumptions about orbital anisotropy. Modeling gas dynamics requires accounting for turbulence and pressure forces. Estimating jet power from cavities depends on assumptions about pressure balance and geometry. Each method carries sources of error, but the convergence of independent techniques increases confidence in the overall picture. In M87, multiple lines of evidence all point to a supermassive black hole of several billion solar masses powering the observed phenomena. The advancement of technology promises to reduce these uncertainties. Future expansions of the Event Horizon Telescope will add more stations and operate at shorter wavelengths, improving resolution and sensitivity. Next-generation X-ray observatories will measure gas motions in clusters with unprecedented precision. Radio arrays like the Square Kilometre Array will map jets and lobes in greater detail, while space-based gravitational wave detectors will directly detect black hole mergers confirming growth pathways. These tools will deepen understanding of M87 and similar systems bridging gaps in knowledge. M87 has thus become a benchmark for the study of supermassive black holes, not because it is unique, but because it is accessible and well observed. The galaxy's proximity brightness and enormous black hole make it ideal for testing theories and techniques. Insights gained from M87 apply broadly to active galaxies and clusters, illuminating how black holes shape the universe. The interplay of accretion jets, magnetic fields, and feedback is not peculiar to M87 but characteristic of massive galaxies throughout cosmic history. At the same time, uncertainties remain that motivate continued study. The precise spin of the black hole is unknown. The exact mechanism of jet launching, whether dominated by the Blanford-Znajek process, the Blanford-Payne process, or a combination, is still debated. The composition of the jet, whether dominated by electrons and positrons, or including a significant proton component, is unresolved. The partition of energy between radiation, magnetic fields, and particles remains under investigation. Each of these questions can be addressed only through further observations and refined simulations. The methods that revealed M87's black hole are also opening windows on other systems. Sagittarius A in the Milky Way provides a complementary case at lower mass, allowing comparison across scales. Quasars at greater distances show black holes in more active phases, illustrating growth at earlier epochs. By connecting these cases, astronomers build a unified picture of black hole physics, with M87 serving as the anchor at the high-mass nearby end. In the broader context of astrophysics, the study of M87 exemplifies how multiple techniques converge to reveal the unseen. Light in its many forms carries information about plasma fields and gravity that cannot be measured directly. By decoding this information with spectroscopy, photometry, timing, imaging, and polarimetry, astronomers make the invisible visible. The result is not only a portrait of a single black hole, but a demonstration of how humanity can probe the most extreme objects in the universe with ingenuity and persistence. The lessons from M87 extend beyond science. They show that phenomena occurring at scales beyond human experience can nevertheless be understood through careful observation and theory. The collaboration that produced the first image of its black hole demonstrates what is possible when global resources are united for a common goal. The continuing refinement of methods promises even greater discoveries, ensuring that M87 will remain at the center of black hole research for decades to come.